Thanks everyone for coming to watch me speak today. So I work at the Wright-Patterson Air Force Base out in Ohio for the Operational-Based Vision Assessment Lab. And today I'm just going to be talking about a software package we've put together that helps any user transform object space to image space. My standard disclosure slide is saying that anything I say here today does not represent the views of the DoD, Air Force, or the US government. Okay, so as I'm sure everyone here knows, I've used stereo devices. High fidelity stereo devices are vital for a plethora of industries. So you have military, and aerial refueling, pilots are using this, training across all industries, things like telesurgery, gaming. And so whether the user is using a stereoscopic remote vision system or a head-mounted device in AR or VR, it's really important to properly characterize the image space because that's the main thing that's going to define the user's experience of using that technology. So we put together what we're calling a 3D distortion modeling or 3DDM tool, and its purpose is threefold. One, to aid developers in visualizing the image space results of their display design choices. Two, once they look at that image space, they can go to the scientific literature and infer the perceptual effects of that space, what the user is actually going to see and how their visual system will react to that imagery. And just validate their design parameters, so confirm their output from that object space input. And just an aside for researchers is there are aspects of stereo space distortions, such as Vergen's accommodation mismatch, that have been studied extensively, but there are others that haven't been. And so this tool will help a researcher kind of iteratively vary an image space distortion and make it easy for them to study said distortion. So our tool uses three models. First, shout out to Andrew. His Woods 1993 model. We also use a Held and Banks 2008 model. And then the most recent is the Gao et al. 2018 model. And so, yeah, I'm putting up their complicated equations here, but all of these models are simply recreating that image space from your object space. And most of them are going to give you the same answers. They only vary slightly. I'm sure most of you are familiar with this. I'm just putting it up to describe possible input and output parameters. This list is not extensive and does not apply to each model, but you can put in things like camera separation, user viewing distance, user interpupillary distance, and then the output parameters that the model is going to give you is that camera convergence distance, magnification, hyperstereo, things like that. Okay. So I'm going to go into how to use the tool and what it can do for you. Some of this I'm not going to explain, or I'll have to rush through it a little bit because honestly the tool does a lot. And so if you get super excited and would like to know more, I will be at the demo session. So come see me then. All you need to run is the executable itself, MATLAB runtime, which is free, and then some system files that we would provide, which just allow the executable to set up each model. And this was developed in the lab, so it's new. It's not the most spiffy or nice GUI, but again, we're just more focused on the math and getting you numbers. But I'm sure maybe sometime in the future we might make it look nicer. So here's your landing page. You just select your system folder, you get your file explorer up, you choose what you want, and then you can choose from any of the three models. You can also open them all at the same time if you like, but it gets a bit hectic. So I'm going to start with the Woods model. Yes, there's a lot on screen. So just kind of, you can look wherever, but I'm going to walk you through a few things. One is you can notice everything's set at 0, and there are no units where those triple X's are. The first thing you need to do in any of these models and the GUIs is go down here, open your digital input and output, select your file folder. If it's new, you won't have any of that up, but you can just hit restore configuration. So I have a nice Woods for SD&A Excel file that just loads in my model. So now you can see that there are my metrics up there, there are numbers up there. You must load in a model even if you want to recreate it completely. It's just so the GUI has a position to start in. So a few things just first I'm going to point out is the upper left. Those are all your input variables up here. Things that are grouped, the convergence group is grouped like that because all of these variables are mathematically linked. So if you change one of them, one of the other three has to change. But you get to pick which one you would like it to change. The other variables down here are free to vary. So I'm just going to show you a little bit. So here I'm changing the camera separation. Convergence will change once I hit enter. But say I like that camera convergence distance, I want to change my toe-in now, or sorry, I want to change toe-in with camera separation. Now I can go ahead and hit new value and that'll change toe-in. And then this just shows you can use the slider bars if you want to just see how things higher or lower values impact your output information. So on the right here is your output information. The nice thing is you can lock any of this too. So if you are really happy with your display horizontal field of view, it'll tell you, hey, display horizontal field of view is calculated by viewing distance and screen width. So you can go ahead and lock it, and then you can change one of them and the other will automatically update. So this is that's very useful if you know kind of what output parameter you're looking for, and then you can see how to customize your input or your object space variables. Okay, we also have, this is just depth plane compression and focus fixation mismatch. That is what we call vergence accommodation mismatch because when we were explaining it to lay people in the military, no shade, I'm sure that's the same everywhere, they didn't understand what vergence accommodation mismatch was. Focus fixation, they understood a lot better. So that's just what we put in the tool. For these particular values, the user just has to decide what depth they want them calculated at. So you just put that in, hit run, and it'll give you those output values. We use these a lot in the lab. If they're not interesting you, just ignore them. If you want to know what they are, come talk to me afterward. Point of interest is one I use all the time when I'm doing the remote vision system work. I can put in any object space axes and it'll give me that image space axes back. And what I love is this right here, which is your screen separation. So when I go in and put all of these variables in our image generator, I will go out and measure the left eye, right eye images and make sure that it's getting that separation. Normally it does. If it doesn't, I've probably entered something wrong. So the math works well for that. I'm just going to show you the imagery real quick. So each model has its own imagery. For Woods, you go down here and you check that, then hit run, and it gives you your nice image space. All of the numbers on the left are what you already put in your main GUI. You can't change them right there. They're just useful to have up if you want to look at them. Then the plot itself is in image space axes. The red ticks are in object space, so it gives you a good comparison of object space depth. You can go ahead and toggle those on and off. We also have focus fixation contours at 0.5 and 0.3 degrees you can show. And then there's a surface data tool which you can choose between percent depth compression or faux fix mismatch, and then it'll show you how that varies across your whole image space. So if you're concerned about discomfort, you might put that faux fix up, things like that. Another wonderful thing you can do is this thing called data point management. You can click anywhere in that image space, and for that exact point, it's going to give you a ton of data. So it's going to give you the axes, the exact point in image space and object space, depth compression, divergence. Again, I'm throwing out a lot of terms here, but it's just to explain the tool. So you can get a lot of information as you click around and explore your image space. Okay, I'm going to go through the rest very quickly. This is just the Helden-Banks model. The groupings are the same. You can input more parameters here, but there's an additional parameters app, so you can put in some of these things like head roll into the Woods model as well. So don't worry about that. The big difference here is image slant calculation. So for the Helden-Banks model, what they do is you define a cube in your object space. And then in your image space, it shows that same cube. So in order to decide on the slant of the cube, they use these weightings from Backus, this Backus paper. It's based on 2 different calculations of human perception of slant. The first one is horizontal disparity and eye position. The second one is both vertical and horizontal disparities. Backus prefers this 80-20 weighting, which is loaded into the tool, but the user has control over. So this might be a fun thing for a research project. I may have suggested it and been shut down. But this is your eye position average, that vertical and horizontal disparity average, the weighted average, and this is the slant in object space. So you have this great comparison here. All right, the next thing is you need to describe your cube in object space, so that just lets you set up your cube, the grid on the cube, the face size of the cube, and where your front face is in depth. You go ahead and run your 3D plot, and you get your lovely cube. Again, you have your surface data, so you can look at how things change over the cube. You can rotate it around. The nice thing you have is you can just pick the sides of the cube you want up. You can also do that data point I showed you earlier. You can pick a side of the cube and click anywhere on it, and it will bring up all that data about that point. A fun thing is you can use live mode. So once your imagery is already up, you go back to your main GUI, you hit live mode, then you can change things like head roll, and then you can see how that user with their head tilted will perceive that cube in the image space. Okay, GAO model, last model. The nice thing about this model is the output is all in ratios. Most of it is in ratios. So it's user IPD to camera separation. It is user viewing distance to camera convergence distance. So the great thing about that is if you're starting to design a system, but you don't know what your camera sensor width is, you don't know what your focal length is, you don't know things, very specific things like that, you can come in here as a starting point. And then another thing that's great is that the imagery, it plots your cube. So this is the original object space cube. It plots your image space cube and the display screen. And it's really easy to update the axes here. So I zoomed in, and then here is from your original object space. Here is your image space cube. So it lets you kind of see your original compared to now what the user is going to see in the space. And again, not everything is going to matter. Not every image space distortion is going to matter. You always have to go back to the literature. But it helps any kind of designer or researcher explore that image space from your object space design. So I use it a lot. We were doing a hyperstereo study recently, so I saw how I could change camera separation and still give the user a nice image space to view while I could vary that hyperstereo parameter. All right, so I think I went over this most. It allows the user to actively explore that perceptual space. It uses 3 models, whatever works best for you. You can compare them, and come see me at demo night.